Hello everyone! I know it's been several months since my last update video, which I think was actually before Thanksgiving. However, I think it's about time that I followed up and filled you all in on what's been going on and what I've been up to. So, as of my last video, the Printalyzer Densitometer finally went on sale, and the first limited production batch actually sold out by around Thanksgiving. Since then, I've built up more inventory, and I'm back in stock, and there are plenty of Printalyzer Densitometer units now available for anyone who wants to order them. I still have components to build more than my current inventory, though I'm waiting on some more 3D printed enclosure components to finish them off. However, I think that project is in a good place for now, and as far as being able to ship product, things are going pretty well. There's been a lot of good reception, and people have bought the densitometer from all over the world, which actually validates my decision to go with USB compatible power source and let users supply their own power adapters. Otherwise, I would need to provide way too many plugs in the box, and it would just drive up costs and make things more complicated. On that front, recently, one of my customers has actually made his own translation of the user manual into Japanese. I'll put a link to that in the description below, which has led to a few sales in Japan, which is the last country to join the list. Also, Greg Davis over at The Naked Photographer has been producing a lot of excellent videos about film testing and sensitometry, where he's been using the Printalyzer Densitometer as one of his measurement instruments. His channel's also worth checking out. As far as this project itself, the hardware is pretty much complete for now. I'm not expecting any changes. On the software front, there's really not much that needs to change in the device firmware unless I get some feature suggestions. Just a few to-do items to just prevent people from miscalibrating things and getting the device into a bad state. But overall, I really haven't had any usability complaints, so there's not much on that list. One last thing I should mention, though, is the companion desktop software for the device. If you notice on the website, it's still showing up very much in a pre-release version number. And the reason for that is I originally envisioned the desktop software as a necessary component for the purpose of getting readings from the densitometer into other software on your computer to perform analysis. However, during development of the product, what it really wound up becoming is a necessary component for diagnostics and factory calibration. If you'll notice, in addition to the tab where the application lets you collect measurements, there are others where you can dump things like raw calibration data or remotely control the device at a lower level than you'd really need to for normal usage. Eventually, though, I do need to fix one or two things in it, maybe add an auto-update feature, bump the version to 1.0, and apply for all the necessary code signatures so that it doesn't throw up as many warnings if you try to download it with the wrong web browser on Windows or something. But otherwise, the real reason the desktop app hasn't seen much love as of late is about halfway through the beta process, the app kind of became irrelevant. So what happened was I realized that since the Printalyzer Densitometer can speak to the computer through USB, and since the USB interface is entirely under the control of the device firmware, I can make it do whatever I want. And what you're really trying to do when you plug the unit into a computer is get numbers from a series of measurements into something like a spreadsheet, so you can do whatever you want with them. Well, it occurred to me, wouldn't it be nice if I could make the device simply pretend to be a USB keyboard and simply type its numbers into the computer? And so the device has now a feature called USB key output, which you can find in the settings for doing just that. It really makes the desktop app completely unnecessary. I also do describe it in the user manual, However, it probably deserves its own dedicated video just to sort of make it clear what you can do with it. So, now for future projects. One thing I've mentioned that I'm working on is a color densitometer as a follow-on. Throughout the development of the current black and white Printalyzer Densitometer, some people have asked about color. Color is an area where the market's really lacking. There's a lot of products that can handle reflection, but almost none that can handle transmission that are not old. Well, doing a color densitometer with the same design philosophy is actually easier said than done. So, the way a lot of the older units work is they have a ring of photodiodes with individual filters on each one, or a single photodiode and a filter ring that you can rotate. And it basically uses this filter mechanism to separate out the different spectral distributions for status A and status M, red, green, and blue, and then visual. Well, that's not so easy for me to do. Getting custom filters for all the right wavelengths and distributions is not that easy, and it would become mechanically complicated. Furthermore, the whole design philosophy of my products is to really see what can be done easily with off-the-shelf components. So, if I make a color densitometer, I would really want it to have a very similar form factor to the currently shipping black and white one. To that end, I am doing R&D along those lines. I've located a sensor that's what's called a multispectral sensor. It has a whole bunch of sensitivity elements all across the spectral range of light color. And I've actually already built a complete prototype around it. The problem is the elements of this sensor do not exactly match what the densitometer isospec calls red, green, and blue. They're kind of their own distribution. And so being able to get readings from this device that actually match your standard color off-the-shelf densitometer is far easier said than done. It's no longer just a matter of calibrating the density range. I also need to calibrate the spectral sensitivity of the light sensor in the device. And that's a very complicated problem. The data sheets and application notes for the sensor don't give a lot of good detail on how to do it correctly. They just drop a couple of keywords and hand wave it. Those keywords being use a monochromator and do a Wiener inverse. Well, that doesn't help a lot by itself. It's given me certain starting points, and I've actually been gearing up to do a lot of that. So I actually have a sort of a fancy calibration setup using a device called a monochromator, which basically lets you steer a light source in sort of narrow wavelength bands across the range, and lets you actually determine the spectral distribution of a sensor. So I have a monochromator and a light source and a whole complicated filter setup with it that I've been using to try to characterize these sensors. But that still only gets you so far, because I still need to be able to figure out how to take data that rig can capture and convert it into a filter that can give me the actual output I need. And I've been doing a lot of work along these lines. I've even gotten a little bit of external help with it, but I'm not really there yet. I'm getting pretty close on, I think, green, blue, and visual, but red is still a bit off, and I think that's due to just some quirks as to how my monochromator behaves. There's this weird spike around the red range where the readings get a little out of whack, but I'm working through it. But even then, Getting in the ballpark's promising, but I really have to get close to exact for this to be a viable product. So just a word of caution, the color densitometer is really not a sure thing. But I am working on it, and it may be something that gets backburnered and come back to once in a while. Another thing users have actually asked about periodically since I started shipping the black and white densitometer is, can it be used for alternative processes and can it measure ultraviolet? Well, the answer to that is no. However, it is a valid question. People working in alternative processes really want an ultraviolet densitometer, and those are kind of hard to find. There aren't that many models that have been made, and I'm not sure of any currently on the market. But it does beg an interesting question. Would it also be a good idea to attempt to develop an ultraviolet densitometer? I haven't committed to doing that yet, but I have started to research the idea. How popular of a product that would be, though, I have no idea. The biggest problem is there does not appear to be an ISO standard for what ultraviolet densitometers are actually supposed to measure. So I kind of have to characterize existing devices and do some guesswork to answer that question. So, I mean, the goal, I would assume, of any such project is to try to match the best existing legacy ultraviolet densitometer that I can get a hold of, but ultimately there's no standard that I can claim that I comply with. But there do seem to be some options. There actually is a sensor made by the same company as all the light sensors I'm using now that is sensitive to several ranges of ultraviolet. And then I would also need to select an LED light source that would emit in the right range as well, once I figure out what that is. And then I also need to decide whether this should be transmission only or if there actually is a use case for doing reflection as well. Reflection is not really any harder, it just means I have a second set of LEDs in the device. Still, food for thought. If anyone has any comments or questions or ideas on the idea of making an ultraviolet densitometer, let me know below. My biggest concerns right now are how many people would want one and what are the actual technical specifications that it needs to comply with. Finally, the biggest project that I've been pivoting back to working on now is the project that originally started all of my crazy darkroom ideas, and that is the Printalyzer Enlarging Timer and Exposure Meter. So this is actually the original Printalyzer. I do get a little annoyed when people try to call my densitometer the Printalyzer, because I see Printalyzer more as a brand name. And it's a brand name because I originally came up with it to name this. Now, this is a much more complicated project than the densitometer electronically, but also much more straightforward in terms of actually building it. I've gotten back to doing a lot of real engineering work for the next prototype, and I'll hopefully show you some clips of what I've been doing. So now we're going to go through the current state of the electronics design for the Printalyzer Enlarging Timer. One of the key changes of this design from the initial prototypes is that I've decided to split the main circuit board in two. So the idea is that all of the digital logic and control circuitry that you interact with as a user, and most of the important functionality of the device, is on one big board, and then everything that has to actually interact with AC power gets put on its own isolated board that can be very carefully designed and laid out. So the first board we're going to look at is that power board. Here is the basic schematic of the board, and I should remind everybody that everything you see here is a work in progress. It's divided into several sections, We have the mains input, which goes through a fuse and a power switch. We have our AC to DC conversion, which generates the 12 volts DC that everything else ultimately taps off of. Over here, we have our relay switching, which is the primary way that the Enlarger and Safelite are controlled. This is a pretty useful all-in-one relay driver over here. It doesn't really need any external components, and then it's directly driving these two 12-volt relays, which go to the outlets. And then here's our connection to the main board. Nothing interesting there. And then finally down here is a section that I've added to this board mainly for mechanical reasons. This is a jack that's going to be on the rear panel of the device that uses a protocol called DMX512, which I consider to be my accessory connector. So the idea is if you have any sort of DIY enlarger control, especially if you're working with an LED enlarger head, this will provide a way that the Printalyzer timer can directly go ahead and talk to your own hardware. There's also a lot of off-the-shelf equipment that speaks this protocol, so it seemed like the most flexible option. It's located on this board because I want this board to have all the rear panel connectors, but for the most part, it's really completely independent circuitry. So now let's flip over and look at the PCB design. Again, I must stress this is a work in progress. I've been nitpicking this design for quite a while and still have a laundry list of things I might want to revisit. But over here is the bulk of it, and as you see, the DMX512 connector is a completely isolated section. It's more interesting if you look at it in the 3D view. So here we have our power input, two power outputs, fuse connector, the XLR jack for the DMX interface. And on the other side, we have our relays, our AC-DC converter, some other protection circuitry, fuse holder, and this is the connector for the power switch. On the current prototype, the power switch wires are directly soldered to the board, but I figured switching over to a connector might make assembly a little bit easier. So that's it for the main board, sorry, for the power board. Now we're going to flip over and take a look at the main board. This is a lot more complicated, and there's a lot more work going on here. So the main board I've actually split up into several sections of the schematic. So here we have, our main microcontroller section, debug connector for programming it, memory for storing user settings and calibrations. Over here we have our interface for the buzzer that's used to provide beeps and boops during enlarging timing, and our display connection. Over here I've broken up into several sub-pages, which I'll just quickly go through. This one is for the power supply. It's where all the connections from that power board come in. We have our power entry over here, which is plus 12 volts, plus the control signals for the relay driver. Down here is the input connections for that DMX512 port I mentioned. And in here we have our power regulators. These are buck regulators. They look fairly complicated, but a lot of that is just because of how they work and how they need some electromagnetic interference filtering on the inputs here. But they're fairly compact, and all these parts put together are really pretty cheap when you add it all up. Cheaper than an integrated regulator. And this spits out 3.3 volts and 5 volts. 3.3 volts is what most of the board runs on, and 5 volts is what's used for a lot of the front panel connections. Next, over here we have the schematic for the user input parts, which is most of the controls on the top of the device. Up here we have all of our button grids. There's several buttons. Some have integrated LED indicators and some don't. And also every button has a panel illumination LED next to it as well. Over here is our rotary encoder. It's an adjustment knob that's to the side of the display. I'm personally not a fan of how so many projects these days use one of these in lieu of all these buttons, but I felt I should have one anyways, just because it can be useful for fine adjustments. Over here we have a connection to a switch that's on the front of the device. That's used for turning off device illumination and safe lights if you want to, so that you can go completely lights out for color printing. And then we have our keypad controller and our LED driver. The LED driver is very flexible in that I can individually turn on and off any of these panel LEDs, which I do sometimes, and it's a nice capability to have. Finally, we're going to look into our front panel connections. This is a part of the project that is currently being actively worked on the most. So up here is the interface for the meter probe. The meter probe is a peripheral attached to the front of the device that's used to measure the light falling down from the enlarger, both for enlarger calibration and print metering. But what's important about this is it needs to be a flexible interface that can handle any future meters or sensors I want to connect to it, and it needs to generally be safe and handle cases like the user unplugging and plugging it by accident while the unit's turned on. So this circuitry is currently very much under development. I've been doing a lot of bench testing of various ideas. But basically, we have an interface that speaks a common protocol called I2C, which I need to do buffering and protection on to make it go over the long wire. And I'm also running it over the wire at a higher voltage than the innards of the device. And I also have similar interfaces for other related signals, such as sensor interrupt and the push button on the meter probe, and then also input for the foot switch connector on the front. With a lot of these, I just need to make sure that everything works correctly and doesn't get messed up by noise and there's no interference issues. And so this is part of the circuitry that I'm still actively working on. There are a few changes I'm still going to make pending some prototyping. Might change some of the components here. Might add some ability to turn this on and off after we're powered up, some protection against overcurrent, so it's a work in progress. And finally, the USB port. I doubt much is going to change here. This is very handy for connecting other peripherals and for using USB memory sticks for backing up configurations. So that's the schematic. We're now going to pop over into the PCB editor, and you can kind of see what it looks like. This view is not too interesting, but the 3D view is pretty neat. So this is the top of the board, which is really the bottom. It's going to be facing downward inside the device. And so here you see, here are the power regulators. Here's the section with the microcontroller, the debug connector. Here's our speaker over here, switch connector, our LED and keypad controllers. Down here we have where the connector is for the foot switch. I'm using one of those audio style jacks because it seemed like the easiest option. Here's the meter probe port. I'm using a 6-pin mini DIN connector, which is very common and should be very easy to get cables for. It also seemed like the easiest solution. Some of the circuitry that drives it, and the USB port here. And if we flip this board over, on the other side, you can see all of the buttons, the panel LEDs, the encoder knob, and the display. So ultimately, this board and the other board need to fit in an enclosure. So I'm going to pop open a different program that's been used for working on the enclosure. And here it is. It has all the necessary cutouts, all the necessary parts. I'm still tweaking the size. Right now, I think it's a little bit bigger than the current prototype unit, but it's from a different manufacturer. I had to make it wider in order to fit the DMX out port on the back, though I might be able to make it a little shorter and reduce the depth a little bit, but maybe only by a few millimeters in each direction, so I'm not sure if it's entirely worth it. But yeah, so this is the enclosure. Okay, so now we're over in our CAD package, which I like to use to virtually assemble everything before actually building it. It's a great way to see if all the parts fit and get a much better feel for how things are going to look. So right here, what I've imported is that enclosure design that I just showed you and all of the associated electronics, and basically put them together. So we can pan around the design and see where everything is. On the front, you see I have the ports all labeled here, USB, meter probe, foot switch, and that blackout switch I mentioned. On the back, we have all of our ports, power input, enlarger output, safe light output, and DMX control output, plus our fuse and our power switch. And on the top, we have all of our buttons, our panel illumination lights, our display, and our encoder knob. So there you have it. That's what's been going on in the world of Dektronics. Right now, I'm kind of bouncing back and forth between the Enlarging timer project and various densitometer-related experiments. And we'll see where everything goes. Until later, bye!